Hello, it's Lauren Gomez. This will be my final capstone presentation on deep learning for respiratory disease classification using chest X-ray images. I will discuss the motivation behind my project, the dataset used, the predictive models developed, findings, and the conclusions reached. My goal was to evaluate whether deep learning models could accurately classify respiratory disease from chest X-ray images to determine which model produced the strongest predictive performance. This project investigates whether deep learning can accurately classify respiratory disease using chest X-ray images. Instead of evaluating a single predictive model, I compared 3 different convolutional neural network architectures. The first was a custom CNN that learned imaging characteristics directly from the training dataset. The other 2 models used transfer learning through the pre-trained VGG16 and ResNet50 architectures. All 3 models were trained and evaluated using the same dataset. This way, differences in performance reflected the model architecture instead of differences in the underlying data. Model performance was evaluated using multiple metrics. These are accuracy, precision, recall, weighted F1 score, testing loss, and confusion matrices for a more precise comparison. Medical imaging is one of the most important diagnostic tools available for identifying respiratory disease. Chest X-rays are routinely performed to diagnose conditions such as COVID-19, pneumonia, and other pulmonary abnormalities. However, increasing patient volumes combined with healthcare staffing shortages have made timely image interpretation more difficult. Artificial intelligence has the potential to assist healthcare professionals by automatically recognizing disease patterns within medical images. The research question for this project asked whether deep learning can accurately classify respiratory disease from chest X-ray images and potentially function as a decision support tool that improves efficiency while maintaining physician oversight. The dataset selected for the project was the COVID-19 radiography dataset obtained from Kaggle. It contains a total of 21,165 labeled chest X-ray images categorized into COVID-19, lung opacity, normal, and viral pneumonia. This dataset was selected because of its large sample size, publicly available labels, and suitability for supervised deep learning classification. Before model development, I verified the dataset to ensure that every image was assigned to the correct class and that no overlap existed between the training, validation, and testing datasets. A stratified data split was then performed, where 70% of the images for training, 15% for validation, and 15% for independent testing were divided. Stratification preserved the original class proportions across all 3 datasets, allowing each predictive model to be evaluated fairly. One challenge identified during preprocessing was class imbalance. Viral pneumonia contained substantially fewer images than the other disease categories, while the normal class represented the largest portion of the dataset. To reduce the potential impact of this imbalance during training, class weighting was incorporated so that underrepresented disease categories contributed more heavily to the loss function. This pre-processing step helped improve the model's ability to learn all 4 disease categories rather than favoring the largest class. Here's a representative example from each disease category that shows subtle visual differences that make automated image classification challenging. After verifying the dataset, several pre-processing techniques were applied before model development began. Every image was resized to 224 by 224 pixels to create consistent model inputs. Image generators were then created for the training, validation, and testing datasets to efficiently feed images into each neural network during training. Several techniques were also incorporated to improve model performance and reduce overfitting. Batch normalization stabilized the learning process by reducing variation between training batches, while dropout randomly deactivated neurons during training to improve generalization. Early stopping monitored validation performance and prevented unnecessary training when improvements stopped occurring. Lastly, learning rate reduction gradually lowered the optimizer's learning rate when validation performance plateaued, allowing the models to converge more effectively. Together, these preprocessing and optimization techniques helped produce stable and reliable predictive models. 3 predictive models were developed to determine which architecture produced the strongest classification performance. The first model was a custom CNN, built specifically for this project. Unlike pre-trained models, every layer learned disease-specific imaging characteristics directly from the chest X-ray dataset. The second and third models used transfer learning through the VGG16 and ResNet50 architectures. Both models were originally trained on millions of images from the ImageNet database before being adapted to classify respiratory disease. Transfer learning often reduces training time while improving predictive performance because the model has already learned general image features. To ensure a fair comparison, all 3 models were trained using the same datasets and evaluated with the identical performance metrics. Rather than relying only on overall accuracy, multiple evaluation metrics were used to better understand each model's strengths and weaknesses across the 4 disease categories. The first predictive model developed for this project was a custom CNN designed specifically for classifying respiratory disease from chest X-ray images. Unlike pre-trained networks, every layer within this model learns imaging characteristics directly from the training dataset. The architecture consisted of 4 convolutional blocks with increasing numbers of filters, allowing more complex image features to gradually be extracted. Batch normalization layers were incorporated after each convolutional layer to stabilize training, while max pooling layers reduced dimensionality and preserved the most informative features. Following feature extraction, global average pooling reduced the feature maps into a single feature vector before classification. A dropout layer was also included to reduce overfitting by randomly deactivating neurons during training. After training, the custom CNN produced the strongest predictive performance out of the 3 models. Testing accuracy reached 91.53%, while precision, recall, and weighted F1 score all exceeded 91%. These results indicate that the model generalized well to previously unseen chest X-ray images rather than memorizing the training data. Overall, the custom CNN demonstrated that a model specifically designed for this dataset could outperform more complex transfer learning architectures and ultimately become the champion model for the project. The second predictive model utilized transfer learning through the VGG16 architecture. Rather than learning every image feature from scratch, VGG16 had previous training on millions of images from the ImageNet dataset. During this project, the pre-trained convolutional layers were retained while new classification layers were added to classify the 4 respiratory disease categories. Transfer learning reduces training time because the network already recognizes general image features such as edges, shapes, and textures. The model then adapts these learned features to the new medical imaging task. The VGG16 model achieved an overall testing accuracy of 90.61%. This demonstrates great predictive performance across all 4 disease categories. Although it's slightly lower than the custom CNN, VGG16 still demonstrates strong generalization, which confirms that transfer learning is an effective approach for medical image classification. The third predictive model evaluated was ResNet 50, another transfer learning architecture that differs from VGG16 because it incorporates residual learning. Residual, otherwise known as skip connections, allow information to bypass certain layers during training. This helps to reduce the vanishing gradient problem commonly encountered in deep neural networks. Deep networks can train more efficiently while learning increasingly complex image features. Like VGG16, the pre-trained convolutional layers remained frozen while new classification layers were trained using the chest X-ray dataset. ResNet 50 achieved an overall testing accuracy of 90.49%, with precision, recall, and weighted F1 score all remaining above 90%. Although performance was great, it was slightly lower than both the custom CNN and VGG16 models. These findings suggest that additional architectural complexity alone does not improve predictive performance when sufficient disease-specific training data are available. The learning curve shown on this slide illustrates how the custom CNN performed throughout the training process. Monitoring both accuracy and loss during training is important because it provides insight into whether a model is learning meaningful patterns or simply memorizing the training data. Ideally, training accuracy should steadily increase while validation accuracy follows a similar trend. Likewise, both training and validation loss should decrease as learning progresses. The results demonstrated exactly this pattern. Training accuracy consistently improved over successive epochs, while validation accuracy also increased, eventually reaching 92.50%. At the same time, validation loss steadily decreased, indicating that the model continued improving its predictions on previously unseen data. The relatively small difference between training and validation performance suggests that overfitting was successfully minimized through the use of batch normalization, dropout regularization, early stopping, and learning rate reduction. These learning curves provided confidence that the custom CNN learned meaningful disease-specific image characteristics rather than memorizing individual test X-ray images. This ability to generalize is especially important in healthcare because predictive models must perform reliably on new patients. The strong agreement between training and validation performance presents the custom CNN as the highest performing model before evaluating it on the independent training dataset. Although overall accuracy provides an important summary of predictive performance, it does not explain where a model succeeds or struggles. The confusion matrix shown on this slide provides a detailed breakdown of the custom CNN's classification results across all 4 disease categories. One of the strongest findings was the model's ability to identify COVID-19. The custom CNN achieved a recall of 98.89%, meaning that nearly every COVID-positive chest X-ray was correctly classified. This is important because failing to identify an infectious respiratory disease could delay treatment or isolation procedures. Viral pneumonia also demonstrated outstanding performance, with a recall exceeding 96%, despite being the smallest class within the dataset. The greatest challenge was distinguishing lung opacity from normal chest X-rays. This result was expected because these categories often contain subtle radiographic differences that may overlap, making them more difficult for both artificial intelligence systems and healthcare professionals to classify accurately. Despite that, the model maintained excellent overall performance across all 4 disease categories. These findings showed the custom CNN learned clinically significant imaging patterns and produced a balanced predictive performance. This slide summarizes the overall performance of the 3 predictive models evaluated throughout the project. While all 3 CNNs performed well, the custom CNN consistently achieved the strongest results across multiple evaluation metrics. The custom CNN produced the highest testing accuracy at 91.53%, along with the highest precision, recall, and weighted F1 score. These results indicate that the model not only classified chest X-ray images accurately, but also maintained balanced performance across all 4 disease categories. VGG16 and ResNet 50 also show great predictive capability, with testing accuracy slightly above 90%, confirming that transfer learning remains an effective approach for medical image classification. The most interesting finding from this project is that the best results produced were by the simplest architecture. Initially, I expected the transfer learning models to outperform the custom CNN because they were pre-trained on millions of images from the ImageNet dataset. However, the results showed the opposite. One likely explanation is that the COVID-19 radiography dataset contained more than 21,000 labeled chest X-ray images. This provided sufficient disease-specific information for the custom CNN to learn directly from, rather than relying on generalized image features. Overall, this comparison demonstrates an important lesson in machine learning where more complex architectures do not automatically produce better predictive performance. Model selection should always be guided by objective evaluation rather than assumptions about architectural complexity. Based on these findings, the custom CNN was selected as the champion model for this project. All 3 models exceeded 90% testing accuracy. Custom CNN achieved the strongest overall performance. Transfer learning models performed well but did not outperform the custom CNN. Lung opacity remains the most challenging disease category to distinguish from between itself and the normal category. Deep learning demonstrated strong potential for clinical decision support. So as established from the beginning of the Capstone project, the first focused on completing all project milestones according to the course schedule. The second was to develop high-performing predictive models, and the third was to demonstrate clinical value of machine learning. Lesson 1, pre-processing played a major role in the success of every predictive model developed during the project. Lesson 2, more complex models are not always better. They did not perform the best. Lesson 3, artificial intelligence requires human oversight, especially for healthcare. An important improvement would be validating the predictive models using chest X-ray datasets collected from multiple healthcare organizations. External validation would provide stronger evidence that the models generalize well across different patient populations and imaging equipment. Future research could also incorporate additional respiratory diseases such as tuberculosis, chronic obstructive pulmonary disease, pulmonary edema, and lung cancer. More advanced deep learning approaches, including vision transformers and ensemble learning, may also improve predictive performance. Finally, combining chest X-ray images with lab results and patient clinical information could produce multimodal predictive models that more closely resemble real clinical decision-making. 3 deep learning models were successfully developed. The custom CNN was the champion model. Testing accuracy exceeded 91%. Therefore, deep learning demonstrates strong clinical potential. AI should be a support tool, not replace healthcare professionals. AI requires human oversight. This concludes my presentation.